Let's do an example problem on chapter 5. So let's say we have a hot sphere. It's a sphere of diameter 100 mm with density 1000 kg per meter cube. It's initially at 475 Kelvin and has a thermal conductivity of 3.5, and the specific heat is given. So the sphere is which is initially at 475 is suddenly placed in air which is at 300 Kelvin and has a heat transfer coefficient of 20 watt per meter square Kelvin. And the question asks us to determine the temperature at the center of the sphere after 250 seconds. And it says that we have to use the radius as the characteristic length. Now this is a transient problem. So the temperature of the sphere will change with time. And if uh, we cannot use the lumped capacitance assumption, then that means that our temperature will also vary spatially, as in our temperature in the sphere will vary in the radial direction as as time progresses. So for that, we'll first have to calculate the Biot number, and the definition for Biot number in this case will be h, which is of the air, r, which is the radius of the sphere, and divided by the thermal conductivity of the sphere. All these values are given and we get the Biot number as 2.857, and it does not satisfy our condition because our Biot number is greater than 0.1. That means that there will be a temperature distribution in the radial direction in the solid sphere, and we cannot use the lumped capacitance analysis to solve for the temperature variation with time. So what we'll do is we'll use the approximate form that's given in the text for the sphere, and the approximate form is for uh, non-dimensional temperature axis, which is which is that your theta star equals to C1, which is some constant times exponent of minus zeta square into Fourier number divided into 1 upon zeta 1 into r star multiplied by the sine of zeta 1 into r star. So zeta 1 here is in radians, so keep that in mind. And uh, now this equation here is only true if our Fourier number is greater than 0.2. Otherwise, we'll have to use the summation of all the terms. So the what I've expressed here is just the first term of the expression which is given for theta star. So for that, we'll first have to calculate the Fourier number to see if we can use the first term only to calculate the theta star. But let's see what r star and theta star are. So r star is nothing but non-dimensional radius. So it's r divided by the radius of the hot sphere, and theta star is T0 minus T infinity, where T0 is the temperature at the center of the sphere at R is equal to 0, divided by Ti minus T infinity. Ti is initial temperature of the sphere. Now moving on, we first we first have to calculate the Fourier number, but we can find the values of zeta 1 and C1 from table 5.1, and the values depend on what your Fourier number is, or in what your Biot number is. So based on the Biot number, the values here are 0.92 and 1.08. So the definition of Fourier number is alpha t divided by r square, where alpha is the diffusivity and it's defined as k divided by rho c, where k is the conductivity of the sphere, rho is the density, and c is the heat capacity, the specific heat capacity of the sphere. This gives us the value of alpha as 2.5 into 10 to the power minus 6 meter square per second. And on substituting this value of alpha in the uh, Fourier number equation, we get, and substituting t equal to 250 seconds, we get our Fourier number as 0.25, That means it is greater than 0.2, and we can use the first term only to approximate our theta star. So our assumption was right. And now the equation for theta star had a sign of r star and an r star in the denominator. So because our r is equal to 0, at the center your r will be equal to 0. Your this expression will be sine of 0 by 0. Now we know that sine of 0 is 0 and denominator is 0. So after you apply limits, this term goes to 1. So this term can be approximated as 1. So we just have to calculate the C1 times exponent of minus zeta 1 square into Fourier number, and we know the value of Fourier number. We know what is zeta 1 and C1 is. So on substituting these values, we get theta star as 0.88, and theta star is nothing but t infinity minus t0 minus t infinity divided by ti minus t infinity, which gives us T0 as 454 Kelvin. So we started with 475 Kelvin, and after 250 seconds, which is almost after 4 minutes, 4 minutes and 10 seconds, the temperature at the center is now 454 Kelvin. So this is one way in which you can apply transient analysis. Another way is, what if our BO number was a very small value? For example, it say the BO number was 0.05, and we can apply the lumped capacitance to calculate the temperature of the sphere. Now, if this condition is satisfied, that will mean that our entire sphere will be at a uniform temperature, as the spatial distribution will be negligible. So our center as well as the entire sphere will be isothermal. So our sphere will act like isothermal body, and it will be at and there will be no spatial temperature gradients. So the entire sphere will be at a single temperature at a particular time instance. So in that case, we apply lumped capacitance, which is theta star, which is t minus t infinity divided by ti minus t infinity. And notice that we don't have a t0 here, and that's because the entire body is at a single temperature, equals to the exponent of minus BO number times the Fourier number. And on substituting the BO number equal to 0.05 and the Fourier number that we initially calculated, which was 0.25, we get theta star as 0.9875, which gives us the temperature at 250 seconds as 473 Kelvin. Okay, so this is another way in which you can solve transient analysis, or it depends on the question. So if you are given your heat transfer coefficient or to characteristic length such that your BO number is smaller than 0.1, then you can use lumped capacitance, and this was just an example to show how will you apply lumped capacitance in that case. Now, another way or another variation for this question can be, you may be asked, okay, let's again assume that you can apply lumped capacitance and your BO number is 0.05. So after what time will the sphere reach a temperature of 420 Kelvin? So initially we were given a time and we had to calculate a temperature, but in this case we are given a temperature and we are asked to calculate the time. So we'll again use the same formula, except that I have written this formula in terms of the definitions of BO and Fourier number. So I've replaced it instead of writing it in terms of BO number and the Fourier number. So in this case, we know what the surface area is, we know what H is, we know what the volume of the sphere is, and we know the density and the specific heat of the sphere. So we just substitute these values, and our T is given to be 420 Kelvin. So we get our left hand side, we know all the parameters on the left hand side, or all the variables on the left hand side. On the right hand side, we have an exponent uh, to the power, we have an exponential term. So to solve this, we'll take natural log on both sides so that we get a particular value on the right hand side. And on taking the natural log on both sides, left hand side we get 0.685, and on the right hand side we get we take the natural log of this equation, and then we get on the left hand side minus 0.377, and on the right hand side we get minus 8.57 into 10 to the power minus 4 times time, which is the expression in the bracket in the parenthesis. And this, on solving this, we get the time as 440 seconds. So after 440 seconds, our temperature, it will take 4, so after 440 seconds, our temperature will reach 420 Kelvin. And we saw that after 240 seconds, the temperature was just at 473, which was just a 2-degree difference. So this is another variation that you can have, and you must be able to, you must be sure how, you must be able to identify what type of analysis you have to do on reading the question. Okay.